All right, so we're starting section 3.2, and then this video is just meant to go over the concepts, and the following videos will go over examples. Section 3.2 deals with what's called Rolle's theorem and the mean value theorem. And that's pretty much basically what the section covers are these two theorems. And so I will present each theorem and then also have an example demonstrating each theorem where it's already worked out, but I'll explain the solution. All right, so Rolle's theorem says let f be a continuous function on a closed interval ab and differentiable on an open interval ab. What it means to be differentiable just means that the derivative f prime of x exists for all values x inside of that open interval. So it's got to be continuous on the closed interval and differentiable on the open interval. Now, if f of a equals f of b, then there's at least one number c in the open interval ab such that f prime of c equals 0. So what it means by f of a equals f of b, that means the endpoints for the interval in which the function evaluated at, if their y coordinates are equal to each other, then there's at least one value c, and this is guaranteed that there's at least one. It could be one or more in the open interval ab such that f prime of c is equal to 0. And so I drew two pictures demonstrating this. The first picture has only one value c, and you'll have, so I have this green curve is the function, and so f of a and f of b, these are the endpoints, and they're supposed to be equal to one another as far as the y coordinates go. And here, c has the tangent line, slope of the tangent line is equal to 0. So that's what it means, f prime of c equals 0. So again, that's slope of the tangent line. And you know, from the previous section where we dealt with critical numbers, this is basically sort of just a critical number. Okay, so that is just one picture where it has one value c that's in the interval between a and b such that f prime of c equals 0. This next picture, I have two values for c where I labeled them c1 and c2. And again, f of a is supposed to be equal to f of b. And so I have a continuous curve for the function, and f of c1, so where c1 is, there's this horizontal tangent line that has a slope of 0, and then there's this other horizontal tangent line for c2 where the slope is 0. Now notice that this is a relative max, and then this is a relative min. All right, so Rolle's theorem just guarantees that there is at minimum one value c in the integral for which the slope of the tangent line is going to be equal to 0, given the condition that the endpoints f of a equals f of b. All right, so that's what Rolle's theorem means. The next theorem is called the mean value theorem. And it says if f is continuous on a closed interval ab and is differentiable on the open interval ab, so that's the same as before, like in Rolle's theorem. And again, differentiable means the derivative exists for all points inside of the interval ab. So if you have these two conditions, then there exists a number c in the open interval ab such that f prime of c equals f of b minus f of a divided by b minus a. So I put in yellow some key points as far as, and then a key difference from the mean value theorem compared to Rolle's theorem. I'll go ahead and just discuss that this main point for Rolle's theorem requires that the endpoints of the interval a and b have equal y values, y coordinates. So in other words, f of a has to equal f of b. That's a requirement that's in Rolle's theorem, but this is not a requirement for the mean value theorem. All right, so for the mean value theorem, we just need for it to be continuous and differentiable. And then provided that's the case, then there's going to be a c such that its derivative equals f of b minus f of a divided by b minus a. Now what this part says, with the f prime of c equal to that fraction, that says that the slope of the tangent line at c, so that's f prime of c, that's the slope of the tangent line, is equal to the slope of the secant line that goes through the endpoints. So a secant line just goes through the curve of the function. It just means goes through it twice, 2 points. And so the secant line that goes through the endpoints has the same slope as the slope of the tangent line at some value c. All right, and another thing is that it says there exists a number c, whereas also in Rolle's theorem, it says exists at least one number c. So Rolle's theorem, I guess, is more precise. I'm not sure the right words, but it gives you that there's at minimum one number c. Whereas this just says there exists a number c. Okay, so those are the conditions, and I drew a picture that represents the mean value theorem demonstrated. And so the endpoints have, so you have f of a and f of b, and I drew this green dashed line supposed to go through those 2 points, and that's the secant line. And then here is c, and this red dashed line is supposed to be the tangent line. And the slope of that tangent line is the derivative at c, f prime of c. And the slope of the secant line is f of b minus f of a over b minus a. So mean value theorem says that the slope of this tangent line is going to be equal to the slope of this secant line. Basically, they're parallel lines. All right, that's what mean value theorem states. Now I just go over 2 examples, one of them going over Rolle's theorem, and then one of them going over mean value theorem. So this is example number 11 in the textbook, and they give you f of x equals negative x squared plus 3x on the closed interval 0, 3. You're going to determine if Rolle's theorem applies, and if it does, find all values c such that f prime of c equals 0. All right, so Rolle's theorem states that we need the function to be continuous on the closed interval and differentiable on the open interval, meaning the derivative exists. And then we have this added condition that f of a equals f of b. So those are 3 things we need to check. And I worked the problem out, and in the solution, I say that your function negative x squared plus 3x is a polynomial. Polynomials are continuous everywhere. Further, we can always find the derivative for any value x for a polynomial. In other words, it's continuous on the closed interval 0, 3, and it's differentiable on the open interval 0, 3. So those 2 conditions are met. Now we need to check that the endpoints are equal. So we need to check if f of 0 equals f of 3. So we plug in 0 into the function, and you get the output 0. Plug in 3 into the function, and then do some simplifying, and it also gives an output of 0. So they have the same y coordinates. So that means f of 0 equals f of 3. So that 3rd condition is met. The endpoints have equal y coordinates. So now that these 3 conditions are met, we can apply Rolle's theorem. So for Rolle's theorem, we're trying to find all values c in the open interval 0 to 3, where its derivative is equal to 0. Now this is similar to finding the critical numbers from the previous section. And we found critical numbers by first finding the derivative, and then you set the derivative equal to 0 and solve for x. So first find the derivative. And so our function's negative x squared plus 3x. So by derivative rules, power rule, this becomes negative 2x to the 2 minus 1 plus 3 times 1, because the derivative of x is 1. So that simplifies to negative 2x plus 3. All right, negative 2x plus 3 is the derivative. Now we got to set that equal to 0. And when you set negative 2x plus 3 equal to 0, solve for x, you get x being 3 halves. And I said, note 3/2 is inside of the interval 0 to 3. And so we're done. We have applied Rolle's theorem, and we found the value c such that its derivative is equal to 0, and that particular value is c equals 3/2. All right, so we check 3 conditions for Rolle's theorem. We got to check that it's continuous on the closed interval, differentiable on the open interval, and then we need to check that the endpoints are equal. Now this next example is the mean value theorem demonstrated. So this is number 39 in the textbook, and it's f of x equal to 6x cubed, and it's defined on the closed intervals 1 to 2. So determine if the mean value theorem applies, and if so, find all values c such that its derivative is equal to f of b minus f of a divided by b minus a. So the conditions for mean value theorem are similar to Rolle's theorem. It's really just the first 2 conditions that we need to check. For Rolle's theorem, we had the continuous and differentiable part. We don't need this 3rd condition. So really we need to check continuous and differentiability for the mean value theorem. So 6x cubed, similar to the previous example, that's a polynomial. Polynomials are continuous and their derivative exists for any value x. So the first 2 conditions are met. It's continuous on the closed interval 1, 2, since it's continuous everywhere, and it's differentiable on the open interval 1, 2 because it's a polynomial, and polynomials are differentiable everywhere. So now that those things check, then we can apply the mean value theorem. So mean value theorem guarantees that we're going to find a value c in the open interval 1, 2 such that its derivative is equal to f of 2 minus f of 1 divided by 2 minus 1, right? Because the mean value theorem specifically states f prime of c equal to f of b minus f of a over b minus a. In this case, our closed interval is 1, 2, so a is 1 and b is 2. All right, so we need to find all values for c such that this holds. All right, so I said first to observe that for the function f of x equals 6x cubed, I go ahead and find, well, what is f of 1 and f of 2? When you plug in 1 into the function, that's 6 times 1 cubed, which is 6. When you plug 2 into the function, it's 6 times 2 cubed, which equals 48. So the right-hand side, which is the slope of the secant line, f of 2 minus f of 1 over 2 minus 1 is equal to 48 minus 6 divided by 1, which is 42. And again, this is the slope of the secant line. That goes through the endpoints. So I found the right-hand side of this so that we need to find, well, what values for c are such that its derivative is equal to this 42 value, the slope of the secant line. So it's similar to what we did in the previous example, except instead of setting the derivative equal to 0, we're going to set the derivative equal to 42. All right, so what I first need to do is find its derivative. 6x cubed, so the derivative by power rule is going to be 6 times 3x to the 3 minus 1, which is equal to 18x squared. All right, so the difference here is I'm setting the derivative equal to 42, whereas the previous one you set it equal to 0. All right, so I set 18x squared equal to 42 and solve for x. So let's just divide both sides by 18. Simplifies to 21 over 9. To get rid of the square, you square root both sides. And recall that if you're going to square root both sides, you have to consider plus or minus the square root. So it turns into plus or minus the square root of 21 divided by 9, which is equal to plus or minus the square root of 21 divided by 3. Since our interval is 1, 2, the only value among these two is 21, square root of 21 divided by 3. That lies inside of this interval. So we discard the negative square root of 21 divided by 3. It's only the positive version. And that's pretty much it. So by mean value theorem, the value for C in the open interval 1, 2, for which f prime of C equals f of 2 minus f of 1 divided by 2 minus 1 is C equal to square root of 21 divided by 3. So the slope of the tangent line at C equal square root of 21 over 3 is going to be equal to the slope of the secant line of the endpoints. All right, so that's pretty much that's the concepts for this section, and I went over 2 examples demonstrating each theorem. The next video I'll be going over examples.